Imagine you're walking across a vast, empty field. Looks normal, right? But what if, hidden deep beneath your feet, there's a secret tunnel? How would you ever know it's there without digging up the entire landscape? For decades, this has been a massive challenge for border security and military defense. But a revolutionary technology is changing the game, allowing us to see the invisible world underground. This is the story of how we're learning to map the unseen. At its core, it's all about gravity. We learn in school that every object with mass has a gravitational pull. The more mass something has, the stronger its pull. So the solid ground beneath us exerts a consistent gravitational force. But what happens if a large section of that ground is hollowed out to create a tunnel? Suddenly, there's less mass in that specific area. This creates what scientists call a gravity deficit, a tiny, almost imperceptible dip in the gravitational field. The problem is, detecting this dip is like trying to hear a whisper in a hurricane. Standard gravimeters, the traditional tools for measuring gravity, are incredibly sensitive. But they're a bit too sensitive. They pick up everything. The vibrations from a distant truck, the gentle pull of the moon causing tides, even tiny seismic shifts. All this noise makes it nearly impossible to isolate the minuscule gravity signal from a hidden tunnel. It's like trying to find a single specific grain of sand on a vast, windswept beach. For a long time, this noise problem seemed insurmountable, leaving underground threats effectively invisible. This is where a brilliant concept called gradiometry comes in. Instead of using just one sensor to measure gravity, a gravity gradiometer uses two sensors, placed a short distance apart. Think of it this way. If you're in a boat, a single sensor would just tell you you're going up and down with the waves. But two sensors can measure the difference in height between the front and back of the boat. This tells you about the slope of the wave you're on. Similarly, the two sensors in a gradiometer measure the rate of change, or the gradient of the gravitational field. Why is this so effective? Because environmental noise, like a distant vibration or the pull of the tides, affects both sensors almost identically at the same time. When you subtract one sensor's reading from the other, all that common noise cancels itself out. What you're left with is a much clearer signal, revealing the subtle local changes in gravity caused by something like a hidden tunnel. This clever technique filters out the background chaos, allowing the faint whisper of the gravity deficit to finally be heard. It was a huge step forward, but the technology was still bulky, slow, and not quite sensitive enough for real-world, on-the-go applications. The next leap had to come from an entirely different field of science, into the world of quantum physics. Scientists in the UK pioneered a device that sounds like something out of science fiction, the quantum gravity gradiometer. This isn't your standard mechanical sensor. Instead, it uses clouds of supercooled atoms. Inside a vacuum chamber, tiny clouds of rubidium atoms are cooled by lasers to just a fraction of a degree above absolute zero. At these extreme temperatures, the atoms start to behave in predictable, quantum ways. They become perfect, identical probes for measuring gravity. Here's how it works. These atom clouds are released and allowed to fall under the influence of gravity. A series of precisely timed laser pulses puts them into a special quantum state called a superposition, where they exist in two places at once. As they travel, their paths are influenced by the local gravitational field. At the end of their journey, another laser pulse recombines them. The way they interfere with each other, a process called atom interferometry, reveals incredibly precise information about the gravitational forces they experienced along their path. Because this quantum system uses two atom clouds, just like a classical gradiometer uses two sensors, it can measure the gravity gradient with unprecedented accuracy and speed. It can detect gravitational changes that are a trillionth of the strength of Earth's overall gravitational field. This isn't just an improvement on old technology. It's a complete paradigm shift. It is like going from trying to see the stars with the naked eye to suddenly having the Hubble Space Telescope. This breakthrough was hailed as an Edison moment, a true turning point in sensing technology. The real-world implications of this quantum leap are profound, especially for national security. Imagine military patrols or border agents equipped with portable, backpack-sized quantum sensors. They can now walk or drive along a border, scanning the ground in real time. The device would instantly map out any underground anomalies, revealing the exact location, depth, and trajectory of clandestine tunnels used for smuggling or unauthorized crossings. No more guesswork. No more costly and time-consuming exploratory drilling. The invisible becomes visible. This isn't just for borders. The same technology can be used to secure critical infrastructure like military bases, government buildings, and power plants. It can detect hidden tunnels, unknown basements, or unmapped utility lines that could pose a security risk. In urban warfare scenarios, it could provide a vital tactical advantage, revealing enemy positions in subterranean networks without putting soldiers in harm's way. It's a powerful tool for preemptive defense, allowing authorities to find and neutralize threats before they can be exploited. But the applications go far beyond defense. In civil engineering, this technology can be used to map the ground before construction, preventing costly accidents caused by hitting unknown pipes, sinkholes, or old mine shafts. Archaeologists could use it to discover buried ruins and ancient structures without disturbing the site. Geologists could map out underground water reserves or mineral deposits with incredible precision. We are literally creating a high-resolution map of the world beneath our feet. From the simple concept of mass and gravity to the mind-bending principles of quantum mechanics, this journey has led to a technology that is reshaping our ability to understand and interact with our environment. What was once the realm of science fiction, seeing through solid ground, is now a reality. By harnessing the power of cold atoms and laser light, we've developed a sixth sense for gravity, turning what was once a fundamental force of nature into an invaluable source of information. The ground beneath us is no longer a mystery. We are charting the unseen, and in doing so, making our world a safer and more understood place. Thank you so much for watching. If you found this journey into quantum sensing as fascinating as I did, don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next deep dive into the technologies shaping our future. See you next time.